So you learned all about the barycenter, the center of mass between Earth and Moon. It's that barycenter that makes a smooth elliptic orbit, and the Earth-Moon system kind of wobbles around the Sun. Okay, so you think you already know the gravitational force, yes, and you have learned that it's between any two bodies that have a attraction between them through this gravitational force, and it is directly proportional to the mass. So if you have a mass of m, there is a force of gravity Fg. If the mass is doubled, then the force of gravity doubles. If it's 5 times the mass, then the force of gravity is 5 times. So it's linearly proportional to the mass, right? So we are going back to the simple Newton's law of universal gravitation. Every object that has mass in the universe is attracted to every other object. Again, when you have two things sitting here quietly, the gravitational pull between them is too small, so they're not going to start moving towards each other. We're not talking about a magnet anyway, we're talking about the gravitational pull, right? So the example of the gravitational pull between the Moon and the Earth then is related to the G, the universal gravitational constant, times mass of Earth times mass of Moon divided by r squared, the distance squared. Okay, what is the distance? Theoretically, we generally assume that it's a distance from the center of the Earth to the center of the Moon, assuming that the masses are concentrated at the center. We will see that that's not the case, that Earth has a finite volume. It's a sphere, several thousand kilometers in radius, so obviously every parcel of mass on Earth is away from the center. It's going to matter. Okay, so here is the sketch of the orbit around the Sun. It's shown as a circle, but you know it's an ellipse. So here it is. You can see the Earth-Moon system wobbling around. In the green line is the Moon, and the blue dot and the red line is the Earth. And you can see that they're going around, and it is this black line, the smooth line, is the barycenter making the smooth path around. And we will see that as the Moon keeps getting on the other side of the Earth, away from the Sun and towards the same side as the Sun, you're going to have phases of the Moon, right? From new moon to full moon and full moon to new moon. So here is the animation that I was mentioning. This is how the Earth-Moon system wobbles around the Sun. Okay, this is what produces the tidal forces. So here it is, the gravitational force. Let's say an astronaut is shown here. He's being pulled towards the center of the Earth with a force of gravity, Fg, that he feels, and it depends on the distance r, because the force of gravity is the gravitational constant G times m1 times m2 divided by r squared. So if the astronaut moves away and the r increases, then the gravitational force decreases by 1 over squared of the distance. So even if distance increases by 2 times, the gravitational force decreases by 4 times. That's something to remember. So if the satellite or the astronaut goes far enough away, you can remember, probably have seen that they become weightless in space, right? That's because the gravitational force has been reduced by sending them into space away from the Earth. Okay, so inversely proportional to square of the distance between the two objects. That is something that becomes critical. And the new thing you will learn is that the tidal force is actually proportional to 1 over the cube of the distance between the two bodies. That's what makes the solar tidal force so small on Earth, because it's so much further away, even though its mass is so much more than the Moon.